sharp. If there's any issues, you can type them in the chat, and hopefully either Marcelo, who's also on hand, or Bruno can help resolve them. All right. So there's a few people still joining as we speak, but we will start, excuse me, any second now. There we go. Good. Welcome, everybody. This is the virtual lecture for the Intro to Supercomputing course. And we're doing these series of courses in the next few weeks as a replacement of our usual summer school, which is 1 week intensive full-day programs in 3 streams. Instead, since we can't meet face-to-face, we're doing these online lectures. And so this is the first one. It's a format that we've not used before, so bear with us if things are a little bit shaky. Let us know if anything is not working. If it's not, we will try to fix it and do better next time. So this first course is about just an introduction to supercomputing. I'll explain a little bit what we mean by it. And you'll get to use a supercomputer. So I hope you're excited. So what we'll do is we'll introduce the basic concepts of what supercomputing is. And it's really meant as a fairly high-level primer. It'll be very useful if you take any of the other courses. Some of the things you'll have to know, some things some of you might already know. We'll talk about the motivation for supercomputing, or HPC as it's also called. Some of the issues, some of the things you can expect from using supercomputers and how they're different from using your own computer. It will be helpful, especially for the hands-on, if you have a bit of familiarity with the Linux command line and editing text files. That is pretty much all we'll be doing in the hands-on part or in the assignment part. If you are not familiar with that, I encourage you to stick around anyway. You'll still learn a lot. But I also encourage you to make sure you either watch or attend the next week course, which will be on the Linux shell. Okay, so what do you need? Well, you need a computer with a browser and internet connection and a Zoom client. Now, if you are seeing this, more than likely you have set that up already, so that's great. What you will also need to be able to connect to our Teach supercomputer, which is the Teach cluster, is an SSH client. If you are on a Mac or in a Linux, you tend to have a terminal application, and that terminal application or console application, whatever it might be called, will have a command called SSH, and we'll show when we get to it how to use it, and you'll use that. If you don't, if you're on a Windows machine, it doesn't standard come with that, the easiest thing to get is an application called MobaXterm, and I've got the link right here. Also very important is that you'll be able to log into the website, we'll do quite a bit of things with this website. The lectures will be on Zoom, but pretty much everything else goes through that website. So let me spend a few minutes explaining what we're going to do on that website. Okay, I'm just going to switch to the website now. Where is it? Here it is. Did that work? I don't know if that worked. No. Oh, yeah. Okay, I think we're good. Okay, so here's the website. Intro to Supercomputing. And the first thing that you'll want to be able to do anything, you'll have to be able to log in. So there's a login button on the top. And you've already done this because you've registered, but oh. No, that wasn't right. That was right. And then when you log in, you'll see your the courses that you're logged into. One of the things that you'll see is an attendance test. We're going to keep attendance. It'll be a very simple test. I'll give you a number, and you have to basically select a number from a list. And I'll give you that in a very short while. The site itself, if you click on it, will have a whole bunch of different things. There'll be a calendar and course events. There's some links. There's a forum, and the forum is very important because rather than just asking questions during the lecture, in between the lectures or even after the course is done, you can keep asking questions on the forum. So if you click on the forum, you'll see here's a forum. You'll have to click on the site has the possibility of multiple forums, which we're not using, but that's why we have to select the forum we want. And then you can ask questions. You can start a new thread and ask a question. So that's the forum. Here are the tests at the end. We're going to have to take an attendance test, and I'll show you that just as we finish looking at the website. There's an assignment Dropbox. So I'll give you an assignment at the end of this lecture, something to basically try your hand at supercomputing with. And again, I'll explain exactly how, but you'll have to upload a file or two files into this part. So that's where that is. Furthermore, on the home part, you'll see the login information for all of the events. And then finally, very important, you want to be able to get into the cluster. You want to know what your login information is. So click on login information. You'll see your username. If you have a Compute Canada account, that username will be your Compute Canada account, and the password will be the same. So you just use that account. If you have one of the TMP accounts for just the education site, this will say something like signet guest and a number, and then a password. And so you use those to log in using the command SSH and then the username at teach.signet.utoronto.ca. I have a more complete explanation, but this is what we have on the site. So you need the site, you need to be able to log in to post to the forum, to give your assignments, and to take the assignment tests. So let's look at the assignment test now. It's open. You'll see there will be one for every day that we have an event. And if you click on it, you can start it. And I'll ask you a question. The question will be, what is the attendance code for this session? So the attendance code for this session is 4, okay, the number 4. So select 4. There are no other questions. And then don't forget to click submit and submit again. And then it said correct. And so now it knows that I was here, or at least Testy McTesty's face was here. So I encourage you all to do that because that's how we know that you're here. And the reason that matters is that we can actually give you credit for being here. If you attend 2 out of 3 events, at least 2 out of 3, because things can go wrong, and submit something for the assignment, you get 3 of our Signet credits, and you can work towards a certificate. If you don't care about those, I guess you don't have to do the test, but we'd still actually like to know that you are here. So, and let us know if anything's not working with the test, but this is how it's supposed to go. All right, so that's the site, and that's pretty much all we need from it. Keep asking questions in the forum. It is very useful, I found, especially for an event that misses the in-person component. Let's go back to the slides. Here we are. Okay, so we have all that. We've got an SSH client to use our account with. We should be set. We should be good to go. So what we're going to have 3 days of events. Each event will be an hour and a half. And during that, you can ask questions at the chat. So the chat is right here. Bruno is there too to answer questions. You can answer the forum, as I already showed. And then, because I'm going to give you an assignment, and hopefully you'll try your hand at it, we set up office hours or hands-on sessions for the next day. So next day, the same time at 12:30 until 2 Eastern time. We're just here, and in those sessions, you'll be able to share your screen if you want to show something that didn't work, or you just want to ask questions, or you just want to sit around and see what other people's questions are. Totally fine. And that can be very useful to sort of get going. Then at the end of that day, we expect the assignment to be done. And you'll see that the assignment is not too difficult on purpose. It doesn't have to be complete. It doesn't have to be fully working. What we really want this for is that I can go and look at them. And the last day, I can look at the common mistakes or common pitfalls that you guys have encountered and correct them. And then I'll also tell you what the solution is. If there's anything that we don't get to today in terms of material, we will also do that. So that last day is really a wrap up. As I said, if you enter the code for the attendance code for 2 out of 3, 3 out of 3 would be ideal, but 2 out of 3 would be enough. And you submit the assignment and you've shown some sort of work, we'll give you your credits. Okay. All right. So that is the admin part of this lecture. Again, if there's any questions, ask them, please do. So let's go into supercomputing then. So supercomputing, or also called high performance computing, some people call it advanced research computing, although advanced is a sliding scale, so is super. But what it means is really looking at solving problems that are too large to solve on your own desktop or laptop or even workstation. So you leverage large multiple computers to solve the computation. And as we will see, that will mean that we have to do things in parallel, or those machines have to do things in parallel. There's no way around it. So it involves quite a few components if you get down to all of the nitty gritty. There's hardware things to consider, algorithms and software, different approaches. But let's first look at why you might need this. Because if you have a research project and your computation takes, let's say, half an hour, and you need to do 10 of those to finish your PhD, you really don't need a supercomputer. You are fine, right? You need a supercomputer. You need high performance computing when your problem takes too long. It wouldn't finish in the 4 years that you've set aside for your project, or it's too big, it doesn't fit, you need more memory, or there's too much data and you need more storage. Those are cases where you have to go and move your computation into a supercomputer. There's a few typical cases. These run a lot on our machines. Anything to do with computational fluid dynamics tends to get really computationally heavy quickly. Molecular dynamics and body simulations, similarly, smooth particle hydrodynamics, which are useful in astrophysics. All kinds of Monte Carlo simulations. Computational quantum chemistry is a very heavy computational problem as well. And especially on the sort of large data side, bioinformatics has become, in recent years, a big user of HPC, just because they have so much data to churn to. And from that, or related to that, really, is the whole data science and machine learning, where, again, there's a lot of data available, and you want to either learn from it or process it. And that just doesn't work on a single laptop. Now, the reason that there is even a lecture on supercomputer rather than just saying, well, no, here's the supercomputer. It is 10,000 times faster than your computer. Just run your system there. This is why there's a problem. Excuse me. Once upon a time, it was actually possible to take a problem that takes too long, wait a year or two, buy a new computer, and that computer would be twice as fast, and your problem would now be solvable. And this graph here shows that. It shows the a couple of different things, but one of the things that we should pay close attention to is the clock speed. That's how fast instructions are handled by the computer. And for quite a while, until about 2005, that always went up, and it went up exponentially. And then something happened. Around 2005, they couldn't make their processors any faster. They run at about 3 gigahertz, and that's pretty much it. There are all kinds of physical reasons for that, mostly heat consumption, and you run them any faster, your chips melt, which is no good. But the solution to this is that you can still make larger machines, but they basically have more hardware and not faster hardware. So they have more chips, but not faster chips. And if you have more, what it means is that you have to keep all these chips, all these CPUs, or all these cores busy. You have to keep them busy in parallel. And so that's where parallel programming and parallel computing becomes essential. Okay, so you might have heard of a thing called Moore's Law. And you'd say, well, this is Moore's Law. I thought it was still going. It didn't die in 2005. Moore's Law is a law that describes a very long-term trend of how many transistors people can make, or manufacturers can put on a chip inexpensively, and that the number of transistors that they can put on a piece of silicon does roughly double every 2 years. And so if you plot the transistors per chip in some sort of units, there's this in a linear log graph, this beautiful straight line, and it went on to I don't have the 2020 point, but it's kind of still going. Although this might flatten at some point too. This seems to be in contrast with the fact that our clock speeds plateaued. And so again, the reason here is not that Moore's Law was dead, but that we couldn't make each of these components any faster. So we got more components, but they were equally fast. So we can get more stuff done as long as we keep all the components busy. We get more cores, but at a fixed speed. Yeah. So that sounds good. More cores, that is faster, right? But unfortunately, you don't just simply throw more cores at a computation. If your computation hasn't been written to be able to use parallel computation, it will run on a single core, and that core hasn't gotten any faster. And to use an analogy, more cores is like having more workers. So suppose that you have a job that has to be done faster, and that's a job done by one person right now, and the HR people have a dilemma. It needs to be done faster, but there are no faster people. You already got the best one, and they can't get any faster. Now, what you can do is hire more people, but that means that they now have to work together. You must change the workflow from what was a one-person job to something where multiple people can actually contribute. And so that involves splitting up the work between the different people, rethinking the workflow process, come up with some communication and administration overhead. And you can also imagine that if it was a one-person job and you suddenly hire 1,000 people, you'll spend more time telling the people what to do than anything else. So at some point, the administration can actually be larger than the eventual work. There's often a sweet spot where the number of people is just all you can have. And so this same analogy holds, or the same principle holds in parallel programming. Most algorithms and codes are written for a single core. It's a program. It says, do this, do that, one step after the other. And now suddenly we have to change that to run things in parallel. Okay, so to know how to code that, how to program these things, it becomes important to know a little bit about the different architectures. It turns out that there's different ways you can run in parallel, different ways you can use multiple cores, and you have to, unfortunately, still use a programming paradigm that fits the architecture. People are working on making that more uniform, but people aren't quite there yet. So let's talk a little bit then now about supercomputing architectures. So the simplest architecture that you can sort of think of as being more machines is to take a whole bunch of powerful standalone computers, could be laptops, could be desktops, workstations, and just connect them with a network. So this picture on the right here is supposed to show that. So we have one node here with a core, and it has a little bit of memory. So the little square is supposed to be the memory. And then another core, and they're connected by wires. And so because I'm just connecting by wires, whatever's running on core 3 doesn't necessarily see what's running on core 2 unless they communicate. So they communicate by giving each other messages. And so the way you would program this is using what's called a message passing interface. So each core acts as its own machine, and then there's some communication between them. These are called distributed memory systems or clusters because the memory is not one big blob, it's distributed over the different workers. It's a very common model because it's fairly easy to build. If you can buy more machines and you can buy a network, you have a supercomputer. And so a lot of supercomputers are essentially of this type. There's another type called multi-core computers, and you see these things in your phones, in your laptops, where in the same machine, in the same computer, there's one big chunk of memory, and you have multiple cores that can work on whatever's in that memory. So now it's a little bit different. Communications between the cores can be done through memory. If core 1 does something in memory, core 3 can see it almost instantaneously. So you program that differently because you don't have to explicitly send messages between the cores. And so this is called a shared memory system. This memory is shared among all of the cores. The way you would program that is with threads, or a very popular way to do this in scientific computing for sure is OpenMP. OpenMP is a technique, and we have a whole week, a whole course dedicated to that as well on how to program these kinds of machines. And this is something that has taken off because it is to some extent easier to program, and also means no network is necessary except what's already in the chip. And so your desktop, your laptops, your cell phones usually have multiple cores at this moment and are going to run like this. This is also what kind of made parallel programming more mainstream, because now to be able to fully use the power of your phone, people have to know how to program in parallel. Before, this was mostly just something done in academic circles and big engineering firms. A third kind of supercomputer architecture are those systems that use what are called accelerators. So accelerators are extra bits of hardware that you stick into an existing computer. So here's an NVIDIA graphics card, for instance, and graphics cards turn out to be very useful in this sense. That they're obviously meant to produce graphics, but what they actually have is a whole bunch of small, not very powerful cores that can only do simple tasks, but have very many of them at the same time. And so these cores in the graphics application would be producing pixels, and all pixels have to be generated at the same time, so that's perfectly parallel. Very nice. Turns out you can also use that power for certain computations. But then, because this is just a thing that you plugged into your computer, and there's the computer and there's this extra accelerator. And so there you have to program the accelerator and whatever computation it does specifically for its different kind of cores. And so you have to do what's called heterogeneous computing. You will start your job on the computer, on the regular chips, and then you will send things over to the accelerator and get them back. And so that kind of programming, that kind of heterogeneous programming or accelerator programming, has a couple of different programming models. CUDA is very popular for NVIDIA chips. OpenACC has is at least an open standard and looks a little bit more friendly. OpenCL is one of the more portable ones, but it is a bit more verbose. In this series of courses in this program, we won't really have time or room to do the accelerators, but there are other resources where you can learn on how to program those. It is a very common bit of architecture in supercomputers because you can get a lot of computation, simple computation, but a lot of computation done from these guys. Now, most supercomputers, and I've got a few examples here, are actually combinations of these. It's hard to buy computers with a single core and then connect them with a network, having pure clusters, because you can't find computers with a single core anymore. Every computer you find has multiple cores. And so let's start with the fastest known supercomputer in the world. So there's a list of the fastest known supercomputers, known because they are self-proclaimed. So there could be secret ones that we don't know about, but they are collected on this top 500 ranking, and it runs a benchmark. And the benchmark is not entirely representative of what you might run on those systems, but it's also not entirely off either. And so you have to prove that you can run at a certain speed in this benchmark. And this a machine called Summit, which is at Oak Ridge National Lab, is currently the fastest known computer. What it has is about 4,600 nodes. So those are the different computers, but each of those computers has 44 CPU cores. That sounds nice already. And in addition, they each have 6 GPUs, so graphics cards, and a whole bunch of memory. And so you've got multiple nodes, multiple cores, multiple GPUs, a network. So basically a combination of all three. And that's how you get the most speed. But they are quite tricky to program. If you have an application that just has to use this kind of speed, you will invest that kind of work. If you don't, then you don't necessarily do heterogeneous computing. Then next, and quite lower in the list, somewhere in the number 60s on the list, is a machine that we have here at Niagara, at SciNet. It's called Niagara. And Niagara is meant for large parallel jobs. It's a cluster. It's currently the fastest supercomputer in Canada. It's not the biggest anymore in terms of the number of cores, but if you run the benchmark, it's still the fastest. And so it has about 2,000 nodes, and each of those have about 40 CPU cores. So that comes up to about 80,000 cores, which is nice, and no GPUs. And that sounds really strange because I just told you that GPUs are the way to get the most computation for your money. And that's true, but when we designed this machine, we actually asked the researchers, do you have code that can run well on GPUs, and do you want GPUs, or do you just want more CPUs and you can get your code to run now? And that comes to the usability issue of GPUs and the programmability. So overwhelmingly, they said, well, we have these CPU applications, they have some GPU applications. We put them together into a benchmark. We basically looked at what machine can give us the most science for our budget. And it turned out that having no GPUs at all for the workflow that we are intended for it was the best thing to do to get the most science done. We did get, in the meantime, a GPU expansion for it. It's called MIST. MIST is very much like Summit, but 50 times smaller. So it really is, you should see it as sort of a trial system in some sort. You can get some useful stuff done. And GPUs, I should say, are very much used these days in machine learning and neural net artificial intelligence computations. And so for those, because there are packages out there like TensorFlow that can use GPUs and you don't have to program them, the adaptation of GPUs is really quick because you don't have to actually go into CUDA programming or anything like that. So if you have AI workflows, these are the kind of systems that you want to look at. If you're writing your own code, though, and it's not AI, CPUs can still be very, very beneficial. And then finally, I need to mention the Teach cluster. That's what we will be using here. It's actually a small part of a previous supercomputer we had here at SciNet. It was called the GPC because we were a lot less inventive in names than now when we call things Niagara. This stood for General Purpose Cluster. So we are so proud of that name. Anyway, that was our old machine. We took 42 of them out when we decommissioned it and replaced it with Niagara. They're still decent nodes. They're 16 cores per node. They have a decent amount of RAM, and they are interconnected through this fast network called InfiniBand. And so you'll be using the Teach cluster in these courses, and we use it exclusively for teaching. And in a little while, I can explain you why we use Teach and not Niagara for teaching. Okay, so those are examples of supercomputers and the kind of techniques that or architectures are there. And each of them comes with different ways of programming it. But in all cases, we have multiple cores that we have to keep busy with some work. So we have some job to do, and we have to split it up. So let's look at that. Let's look at parallel processing. Having a task that has to be distributed over multiple cores. So the main thing to look for when you're trying to do parallel processing is a thing called concurrency. Concurrency are things in your task that can run at the same time. Now, in a very general setting, this doesn't have to be one single task. When you are looking at this Zoom meeting, you could at the same time be running an email client, and they would be running at the same time concurrently because they don't have anything to do with one another. But in general, for scientific computing, we have a computation that has to be done, and it's more intricate. Things do depend on one another. So you have to find within that computation those things that can be done concurrently, so independently. There must be many such parts for it to be efficient, because if you have say the 40 cores in the Niagara node, if you don't have 40 things to do at the same time, you are going to waste some cores. It should also not matter in what order things are done. That is kind of implied in the independently, but it is often surprising because those cores might run just a fraction of a microsecond slower than the previous one. And so order shouldn't matter here. And what limits the possible concurrency is when there are dependencies. So if I say I'm simulating the weather over Canada, what happens in Toronto influences what happens in Mississauga, and therefore there's a dependency of data. That is where you have to do a lot of thinking of what can in your computation be done at the same time and what cannot. Okay, so let's look at the simplest case where we don't have data dependencies, and we can call this a parameter sweep. It's the sort of the best case scenario for doing parallel processing. The idea is you have a model that you have to compute through and get an answer out of. And there's a parameter in that model. In this slide, it's called mu. And mu varies from 1 to 4, but we have many more cases to do. And then depending on that parameter, the computation goes and produces an answer. Each computation itself is independent in this case because it's the same model, but with a different parameter. And so if you run this with, say, 4 cores at the same time, they can run at the same time. So I'm going to show a bunch of these kind of diagrams. And in all cases, the time is supposed to run from the top to the bottom. So it takes some time to do mu equals 1 and gets an answer. It takes some time to do mu equals 2 and get an answer. But we're doing 4 at the same time in this picture. This way, we just get more done. And if you have more computers, we can get even more done. We just give them more stuff to do. A way to measure how much you get done, how useful this is to look at a thing called throughput. So throughput is how many tasks you can do per unit time. And so we can imagine that we have a number of tasks, n, and it takes a certain time t, and the throughput is just we're doing n tasks at that time t. I mentioned this because it doesn't really matter how fast we do each of the tasks. If we can't do them in parallel, we're not getting throughput. We have to do them one after another. If we can do them in parallel, we can. So the throughput is really how much output are you getting per second. And that also then will influence how many cases you can do and how fast your project will end. So if you have independent tasks, like in the parameter sweep, rather than doing a serial process where each of the cases, these blue circles are supposed to be the cases, is done one after another, you put them in parallel. And this should not be surprising, but when you do them in parallel, they become 4 times faster. Now, just to keep with introducing some symbols, P is the number of processors here, and N is the number of tasks that I want to do. If each task takes a time T1, then the total time is N times T1. The throughput is 1 over T1. I do one task per T1. Whereas if I do them in parallel, the throughput becomes P times larger. Okay, so in this case, P would be 4. It's 4 times faster because I get 4 times as much done. These tasks themselves are not 4 times faster, right? I just get 4 times as much done. So this idea of having of seeing how well something parallelizes is called scaling. You take a task, you throw one processor at it, one core at it, 2 processors, 3, 4, 5, 6, and you see how the number of tasks per unit time, so the throughput scales. And in this case that I just presented, as many processors I have, that much more stuff gets done. And this we call perfect scaling. Ideally, that's what you want. It won't be always what you get, as we will see. Another way to say this, and in this picture it looks pretty much the same, is to look at the speed up. It's not exactly the same, but the speed up is how much faster your given problem is solved as you change the number of processors. So the speed up always supposed to start at 1, although for technical reasons sometimes not. One processor has a speed up of 1, and then you see as I add more processors how much faster it is. So technically, to express that, you can take the time that it takes for your serial process, so doing them all at one at a time, divided by the time it takes for pre-processors. And ideally, P-processors or P-cores would be P times as fast. So this should be proportional to P. Then you have linear scaling of your speed up, and that's exactly what you want. For these kind of parameter sweeps where everything happens at the same time nicely, you get this kind of linear speed up. And because it kind of happens easily, people call this embarrassingly parallel. That is, you didn't have to think very hard about the computation to get it to parallelize. You'd still have to do something to make them run at the same time. And it depends on what kind of machine you are, how you do that. But it's not terribly difficult. But that's the ideal case where the computations have nothing to do with one another. So let's look at a case where this isn't so. Say we have some tabulated experimental data, say the temperature over Ontario, which is rapidly rising right now. And we wanted to know, say, the average. We'd have to sum up the temperature of all of the sensors that we have. So now that's good, but we can split this task up where we get different regions summed up by a different processor or core. As you notice, because we're not looking at specific architectures yet, a process, a core, a CPU, a worker, they are all pretty much the same thing. This is a rather abstract notion at this point, so here I've called them processors. So what we need to do is separate up the region into subregions, and each of the subregions will sum up their own sensor data, but the sensor data supposedly is collected somewhere, and so we have to collect it, we have to then partition that data and give it to the different processors to act on. And then at the end, we have to sum them up once more, all 4 of them, and get the answer. It sounds like it is fairly parallel and very similar to before, but there are some parts here, namely the partitioning and the reduction, that aren't entirely done in parallel. In fact, the simplest way to do this is just one by one, give each of the cores a bit of work to do, and one by one, reducing them to a single number. So we can distinguish how much time is spent in the part of the algorithm that can be done at the same time, that can be parallelized, and the part that cannot. So the part that cannot is called the serial part. So partitioning the data cannot be done in parallel. You could come up with things that it is quasi in parallel, but let's say it's not at all parallel. And say with reduction, so we call that T sub S for now. And then the total time it takes to do these parallel regions, so the time it takes to do region 1 plus region 2 plus region 3 plus region 4, we call the parallel time, the time for the parallelizable part. So we want to know how long it would take if we ran that whole thing on a single computer or a single core. Okay, so I'm introducing these these symbols because we can now figure out, knowing that there is some serial fraction of the workflow and a parallelizable section, we can actually manipulate this a little bit and figure out some interesting properties of the theoretical speed up that we can get. So the speed up is the time it takes for one core, so that is TP plus TS, or for P cores, where the TP part is divided by P, right? It's distributed over P. And then by defining the serial fraction as the time for the serial part divided by the total time when run in serial, we can actually write that in a fairly compact form that only depends on the serial fraction and the number of processors P that we throw at it. And so if you plot that for a fairly modest serial fraction, say 5%, as a function of the number of processors, we see something quite interesting. We would want a linear scale up like the blue line here. And what we get is fairly quickly, this diverges from it. And we only get about half as much speed up by the time we're using 16 cores than we would hope for. And it's just a small amount of the computation that is this. So, and it's kind of worse. If you try to see what happens if you throw infinitely many processors at this, you find that your speed up is 1 over the fraction of the serial fraction. So in this case, I guess it would asymptotically reach 20. This is not very strange if you think about there being a part that is purely serial. All of the other part, the TP part, disappears when I throw infinitely many cores at it, but TS still has to be done. So it never gets any faster than TS. It's impossible. It's still there. So what you want to do, because the serial part will dominate how fast you can actually run at the same time, is to make the serial part as small as possible, or to parallelize as much as you can. So, and no matter how big IP becomes, there will be a point where it just doesn't get any faster. There's no point in throwing extra hardware at the problem. You just don't throw extra cores at your problem because you have a serial fraction. And so that's the realistic case. That's what happens. But sometimes you're lucky because you're not interested in just this toy problem. You want to really simulate a large system. And the larger a system is, the better it parallelizes. Just imagine in our reduction problem, the regions become bigger if we have more sensors, but the distribution part just takes as much time as the number of processors we have to distribute. So the serial fraction, when you have a larger system size, a larger number of points, larger data, tends to asymptotically go at 1 over n. And if you plot that, you see that for modest number of size, and these are arbitrary units, you see that as you increase the size, you get closer to ideal. Now, if you again increase the number of processors and you increase the x-axis, you'd see a leveling off eventually still. But it does mean that there is some truth in that if your system is big enough, it will be worth parallelizing. So it's not just the algorithm that matters, it's also the system size. People that want to study how their algorithm ideally scales when the system size is big, they do weak scaling. So what we looked at before is strong scaling. You keep the system the same, the computation the same, you increase the number of processors. In this case, for weak scaling, you increase the size of your system as you're increasing the number of processors. So your n, the size of your system, is some small n times p. And if you do that, you can look at whether the time it takes to solve a system which is twice as large and has 2 times the same cores, whether that time does not increase. So, and with n large enough, you always get this perfect weak scaling. And that's a different law called Gustafson's law. And he said, well, Amdahl might be true, but if you take a large enough system, eventually you get good scaling. Okay, there's other non-ideal cases that we can look at. One other problem that can arise from not ideal situations is a thing called non-locality. And this is hard to describe without going into the hardware. So we'll look at some examples. But what it boils down to is that communication between the cores is slower than computing by the cores. So what I must do to be able to get the most out of my computation is to make sure that basically the data that I need for computation is near the core that's going to do the computation. That's called locality. So if it's a core that generated some data, it should also be the core that works on it. Otherwise, I have to move things back and forth. Memory storage systems, they tend to hide this locality. So there are caches and things that pretend like there is no issue with locality, but now it really depends on how you access the data in your application, on whether you are doing this efficiently or not. And as I said, this is more easily explained with some examples, but you can never completely eliminate this. You need communication in the case of the reduction. You need to sum everything up at the end, but you can minimize it. So if you have this shared memory system, make sure that the data stays to the core that was using it last. In distributed systems, you don't want to have to communicate data from one machine to the next, one node to the next. Try to compute on the data that you have and transmit as little as possible. When you're looking at file systems and memory, accessing things linearly helps. These caches that are hiding things are counting on you to read a file from beginning to the end and not jump back and forth. Likewise, if you have a lot of little files, that is kind of like jumping back and forth on your system, on your file system. And so that is also not bad. It also is bad in other I/O issues. So you want big files and go linearly. Reusing data. So if you already had the data read in, and you have some more computations to do, make sure you do all the computations of that data first before you read in the next chunk. So the trouble with this one is that a lot of these things are hidden, and you can only change them by changing the data access pattern rather than actually coding things differently. But it is a big deal when you're doing data intensive computations. Okay, and then finally, and something we'll look at in more detail, especially for the assignment, is a thing called load imbalance. So let's imagine that we have an ideal situation. We have 32 computations to do, and they're all independent. This is going to scale perfectly, wouldn't it? But there's a catch. Right now, in this case, the different computations, these 32 different computations, take very different times. So some of them are done quickly, and some take a longer time. And let's say that we do not know how long they will take. That part of the computation is figuring out how long they will take. The problem here is that, say we want to run this on an 8-core machine. So we want to run the computations on 8 cores. Well, that's easy. They're all independent. So we just run 4 sets of 8. So here's a little diagram that supposedly explains that. So here's time again. Time goes to from top to bottom. And then there's 8 cores that are each given a task to do. Core 1 here gets a task and it's done pretty quickly. Core 2 got a bigger task to give, to handle, etc. Once the first set of 8 is done, I start a new set of 8. And so I run 8 more, and again and again. So that's great. They run all in parallel, as you can see, and that's nice. However, you might also see that there's a lot of empty space there, and empty space is bad. Right, so here's it again on the left side. If you look at the amount of blue versus unused space, you see that only 42% of the potential computation time has been used. And if you look at the speed up that we got from using 8 cores versus 1, that actually translates to a speed up of only less than 3.5, rather than the 8 that we might want to expect. And it's because load imbalance, right? It's because some tasks take shorter, and therefore these cores have less to do. The load is not evenly balanced. We can fix this though. It's not that difficult. we just give a new task to a core as soon as they're done. And what you get then is this kind of picture. So the same originally 8 tasks are given to all the cores, but as soon as I think this guy finishes first, this core finishes first. So as soon as it's done, the next task, which was a task over here, is given to it. So as soon as a core is not doing anything anymore, it gets a new task. And by doing that, we sort of stack them up better, much better, in fact. And in this case, we get 70% used. And the reason we don't get full usage is at some point we're just out of jobs to do. If we had more jobs to do, we'd probably get a better utilization still. The speed up again is now something more acceptable. And because we don't know how much this is, it's not entirely wasted space. It is what it is. It's what we wanted to compute. Now, we could code these things in ourselves, but there's already a tool that does that. And so towards the end of the lecture, we're going to look at a tool called GNU Parallel. They can take a bunch of tasks and stack them up exactly like this. I've got the citation for this tool right here. If you use it, the author asked that he be cited, and you should. Now, before we do that, though, let's take a step back and explain a little bit why we care. We have this supercomputer. It did this in a reasonable amount of time. It's still 3.4 times faster. Maybe that's enough for us. Maybe we don't care. Maybe we don't need 5.8. But we care. We the people that maintain and service and support supercomputers. Why do we care so much about this efficiency? So this all comes down to the fact that when you leave your laptop or workstation, you go to a supercomputer, it's not your supercomputer. It's a shared and it's a remote resource. So you can't just have a supercomputer. You're going to have to share it, right? There's very few people that can just buy a supercomputer on their own and then be happy. If that were the case, it's your problem if things are not efficient, right? But these days, and partly because of the internet, you can access the resources remotely. So we can build an 80,000 core supercomputer and have hundreds of people use it at the same time. Sharing is good because sharing gets better utilization. If all these cores are busy, that's better than having your own supercomputer because half of the time you wouldn't do anything because you're writing code. And so it's all around better. And just to give you an idea of how much better it is, our large parallel machine, Niagara, its utilization typically lies between 94% and 98%. And there's always jobs in the queue. So the fact that this is not 100% is really because somebody wants to use a big chunk of the machine and it's not all available yet. So it's just some cores being collected. Now, this does come at a price, this sharing and remoteness. Because they're remote and because they're shared, these machines need to be used a little bit different, or actually quite different from how you might use your own computer. And so let's go into that as well. So the first thing is that it's remote. And some nomenclature comes in here. You're at your computer, right? Right now, you're probably at a laptop or a desktop, maybe on your phone. You need to connect to the supercomputer, and the supercomputer is somewhere in a data center. And so the supercomputer will be called the server. And you're accessing that server by connecting through it, through a thing that we will call SSH, stands for Secure Shell. And so you connect and you are what's called a terminal. The computation doesn't happen here. You are just steering it remotely. And in fact, that's why this is called a terminal. What we think of a terminal these days is a window where you type text commands. But it really that's always been the case. But the reason it's called terminal is the last end of your supercomputer. Now, you must communicate with your supercomputer using the command line. It doesn't speak GUI. GUI would be hopelessly slow over this line. It'd be inefficient anyway. And truth be told, nobody uses a GUI in HPC. When you have large computations, you'll figure out how to do them in the command line. And it actually, once you get used to the command line, it is a very powerful tool and much more expressive than mouse clicks could ever be. So it's a nice tool to have. But in this case, because it's remote and because nobody uses them, you'll be using the command line just for that reason. So if you wanted to access this SciNet Teach cluster, which you can if you're registered, then this is how you would do it. You would have to open a command line terminal. So if you're under Linux or on Mac OS, open the terminal application, whichever you like. If you're in Windows, download MobaXterm. PuTTY would also work. There's other ways you could use the Linux subsystem. All of that is possible. This is a very easy one because you also get an X server at the same time. And it's also fairly quick to install. Once you're in the terminal, you type in a command because this is the command line. So you type in SSH, your username @teach.scinet@utoronto.ca. The $sign here is a placeholder for whatever your prompt looks like. So this depends on where you are. And then once you're in, you're in. Now, if you want to transfer files, that also has to be done remotely. And so should you be on the Teach cluster already and you want to download something, there's a wget command. It's useful to know. But if you want to copy things from your computer to the supercomputer, you have to use another utility. And it's called SCP for scopy. And so that both of them are remote ways to interact. SSH will give you a terminal that runs on the supercomputer. That supercomputer doesn't know anything about your computer. So once you've done that, once you've logged in, you can't see your files anymore. So you're going to have to transfer your files first and then SSH in. The account information, just in case this wasn't clear, is also on the course website. So let me just quickly go back to that and make sure that that is understood. Let's see. It's this one. Okay, so on the right here or at the home screen, there's a link called login information for the cluster. That's the Teach cluster. If you click on it, it will say what your username is and what your password is. And then you can log in with SSH. The -y option is optional for this session, and then your username @teach. So if you do that, you will be logged in. Where's my, here. Here we go. Okay. Now, I'm mentioning the transfer files, and that's all I'll say about it, is that you'll need this because when you do your assignment, you will do your assignment on the Teach cluster. Then you're supposed to copy off your results to your own computer and upload them to the website. And so that will have to go through your computer. You have to get the files to your computer and then put them into the site, into the assignment Dropbox. Okay, so that's the remote part, and that means learning a little bit of Linux command line. It's also a shared resource. You share it with all the other people in this course and some other courses. That's for the Teach cluster. When you're into Niagara, when you're logged into Niagara, you share that login node with a bunch of users of Niagara. It's kind of like it's a similar node to all of the other nodes in the cluster. So a cluster is made of nodes, right, as we said. But this part is shared. In this node, or on the whole cluster, you have a couple of directories. One is your home directory. It's called $home, and a Scratch directory, $Scratch. Home is small but backed up. Scratch is large but not backed up. This is where you do your work. These are actually variables, so there's a real location on the file system, but using these variables is useful. All the other nodes of a cluster are called compute nodes, and you cannot log into them. You can't SSH into them. You can't interact with them directly. Instead, you have to write job scripts. So part of the sharing is to basically, you put in an order. You say, I want so many nodes for so much time with these properties. And then on those nodes, I would like to run this particular computation. That you put in a job script and you give it to a thing called the scheduler. The scheduler will take your order, look at all the other orders for resources that are there, figure out who should run first, where there is time, where there is space, and run them for you. Okay, so it's the scheduler's job to allocate the compute resources to your job. The scheduler that we use on Teach is the same that we use on Niagara, the same that we use on many other supercomputers. Pretty much all the supercomputers in Compute Canada run Slurm. So that gives a certain amount of syntactical uniformity, but Slurm has a lot of options. And so you should always dig into the documentation of each supercomputer to see what are the options that are possible for that particular machine. Once you have your job script with the options that you want, with the resource request and the computation, that's called the job script. You give it to a command called sbatch. It puts it into the batch queue. Basically, it gives it to Slurm, and Slurm eventually runs this. Now, let's do that. And if you can find your login information, you can follow along with this. You could try it later as well. That's fine. But let's try and submit a job to the Teach cluster. So we're going to log into the Teach cluster, which means we'll type SSH username at Teach. The username comes from the website. We'll change to the Scratch directory. It's a good idea to run all your jobs from the Scratch directory. This is where you should do all your work. Then you can copy the material for this course. So on the Teach cluster, there's a special path, SciNet course SS 2020, because this was supposed to be a summer school, /1_intro HPC. That is a directory, and you can copy that whole directory to your Scratch, so to $Scratch. But to do all of the files in the directory, I have to say that I have to do this recursively. That's what -r here stands for. Once I've copied over, I have my own copy, and you can edit it. Change directory to this directory that you just created by copying. And then you can submit. In this directory, there is a file called sweep_bondbreak.sh, and you can give it to the sbatch command. And then you can see, once you've submitted it, if it's running by using the sq command. And sq will show you the whole queue. So if there's many users and many jobs, this will just go past you very quickly. If you just want to see your jobs, -u $user will work. And once it's done, it will have created a number of files in a directory called out, but also a file called sweep_bondbreak_output.txt. So I'm going to start this, but I won't finish it because it takes a while to run. But let's try this. Okay, so here I'm going to have to SSH in to the Teach cluster. Let me just do a band. SSH. Oh, that's fine. SSH. I think I am SciNet guest 01 on the Teach. SciNet toronto.ca. And that's going to ask for my passwords. So this is where you look up your passwords. And I'm in. I'm going to change directory to Scratch. You can see the real directory name of Scratch. Doesn't really matter. I already copied it once, so I'm going to remove it just to show how it goes. Okay, nothing's left. Then you can copy SciNet course SS 2020 /1_intro HPC into your Scratch directory. And you can do so recursively. There we go. And then I cd into that directory. I can list the content, and you see this sweep_bondbreak.sh, and that is already a job script. So I can sbatch that, and then I get a number back. So it says submitted batch job 86379. And if I do sq-u $user, I see that I am in the queue. After a while, you get used to what the different things are, but this R here means it's actually already running. Nobody else was running much yet, but I see quite a few of you have tried it. Nice job. And they're all running a single core on this machine. So congratulations to these people that are already running it. You've just run on a supercomputer. Now we'll let that run. We'll see in a little while what the output is, but what is it really that we're doing here? What did we compute? What is this thing? Right? Nice, we're running on a supercomputer. What are we running? So what we're running is a simulation of a chemical bond breakage. So there's a, the script itself runs essentially a parameter sweep for an app called Bond Break. Bond Break is an application that does a simulation of a chemical bond. It's very hypothetical. That's not a real bond. But imagine there's two atoms. There's a bond between them. And by fluctuation, it can break. And so it simulates the motion of these two atoms until the breakage point. And then it prints out what the breakage time is. And that's great. So we want, now that's going to depend on a couple of parameters. And so, by the way, this plot on the right here is the potential energy or the free energy landscape of this model. As a function of bond extension, the system likes to be in this area. That's when it's bonded. The bond extension is finite. But if it manages to go over this hill, it escapes to infinity and it basically is unbonded. So we're starting it off somewhere in here and see how long it takes to go over. So what matters is where we started. So that's x is the initial start. And what matters is how big the fluctuations are. And that's set by the temperature T. So those are two model parameters that we really want to sort of sweep over. But in addition, because this is a Monte Carlo simulation, because there's time steps involved, it does one step at a time, there's random numbers involved, there's other parameters too that need to be set. And so just for completeness, these are the parameters that this app needs. It needs a time step dt, a maximum time to simulate. So imagine that it stays unbroken for like a week. We don't want to compute anymore, we just give up. So there's some maximum time we set it to. A random seed that determines what the randomness is like and that we can vary as well. And then there's some output. So there'll be a file of the data of the position or the bond extension as a function of time in the DFN parameter. There'll be we won't want to write it every time step. There's too much data. So there's another time step dt for output, ODT. And then finally, a file name to write log messages to. That just sort of gives us updates on where we are in the simulation. So these are the ones that are physically important to us and to know. These are things we have to set to be able to get a realistic model. Now they're all set already in sweepbondbreak.sh. So let's look into that job script. So here's the job script. And we'll go through it again step by step. The first line is more important than you might think, but it just says this is a bash shell script. So there's different flavors, dialects, languages that terminals and consoles and shell scripts use. Bash is a very common one, and it's the default one on our computers. So that's the one. But if you don't say that this is a bash shell script, the Slurm scheduler is going to say, I do not know what you want me to do with this, so it will reject it. So you have to say this is a bash script. And then a couple of lines here. They all start with pound sign as batch. Pound signs in normal shell scripts mean a comment. In job scripts also, except if it's pound s batch at the top of your file. In that case, it is actually the specification of your resource request. So we're requesting a single task, which means we'll get a single core for 20 minutes. And then in addition, we want the output to go to a particular file. So we've given the name of the file here. There's a lot of other options you can put here, but for this case, these three are enough. And then the rest of the script is not a resource description, but it's actually the computation we want to run. So the first line that you will notice is a command called module load Python. I choose in this lecture to not go into the module system too much, but there's a lot of software that people need on supercomputers, and the different software packages are in conflict. You cannot install them at the same time. Although you could put them on the file system, but you can't make them accessible at the same time. So the module command just makes those things accessible that you want. So you pick and choose. That means that if you log in, you see very little software until you do module load and then the name of the package. You can look at the docs wiki to know more about it. But what we need here is only Python. We need Python because it turns out that our application bond break was written in Python. And might not be the smartest choice in terms of speed. Come to the Python for HPC lecture to know why. But it was something that I could put together in an hour, and so that was good for a lecture. So we load Python so we can run bond break successfully. Then we have our parameters, and I kind of explained what they mean, and the comments here say it as well. And then we have to run over different cases. So we have to run, in this case, 96 repeats. We're going to try things again with different sets of random numbers. So we're going to start our bonds in the same length with the same temperature and just see for different cases how long does it take. We'll print out a repetition number, and then we call this bond break with all of the parameters. Okay. Now, because we have different cases, we want the output files to depend on the case and on the temperature. So those are encoded into the file names. They all go into a subdirectory out that has a bunch of data that will contain a lot of data. I don't want to see that data. When you submit your assignment, please don't give me anything from the out. It just clogs up the website for no good reason. What we need is this sweep bond break output. Okay. And then we're going to time. So we pass the parameters to the bond break app. We will also time it. We want to know how long it takes. And then the last line is a bit of Linux magic, and that finds all the lines in the output that say that a breakage is detected, and then prints just the time. Again, if you go to the Linux course next week, you might learn a little bit of how this works, but really it just collects all of the breakage times. That's all it does in a nice little line. Okay, so resource request and computation, and this computation has a number of repetitions of essentially the same thing, but with different parameters. Okay, so we want to give this to the scheduler. Our scheduler is Slurm. Why? So we need a scheduler to be fair to all users. There are hundreds of users on Niagara, and they would all like to run as much as they can. If we just let them log in to random compute nodes and run things, then the first people that come would get all of the resources, and that's just not fair. So now we could divide them up and say, you know, this node is for this user, these nodes are for that user, and do it that way. And that would be fair, but then it's not much different from having your own small supercomputer in your lab, and we know what happens to them. They're not used half the time. So that would be a waste of time, and not just a waste of time for those resources. As other users, you would want to use that wasted time. So instead of that, instead of having these fixed reservations, what we do is scheduling things. You submit a job, you say how many resources you need, and the scheduler tries to fit all of those things in basically a space-time diagram, and sees where things fit. Okay. Now, as I already mentioned, on most supercomputers, there's always a queue. There's always more requests than our cores, which is good, because it means we can keep this system busy. But it also means that pretty much always you will have to wait. You submit your job, stuff is already running, you're going to have to wait until it's your turn. But that also will make it fair. Okay, so this is a big difference between running on your own computer, where you just run whenever you want. The economy of scale dictates that you will have to wait. Now, another thing to keep in mind here is that the scheduler is not infinitely clever. A scheduler for a cluster is hard, and it takes time. There's a lot of different factors that come into play, and I will list them in a second, that for these hundreds of thousands of jobs that people submit, because we have so many users, it takes time just to order them and see who's next. Okay, and so to make that even potentially possible to be done, such that if you submit a job, it doesn't take a day for the scheduler to figure out even when it would run, we limit the number of jobs that you can run. And this is a common practice. But it also means that if you have very small jobs, like something that takes a second or two, computing when it would run for for a whole minute, like just computing where it would run and then running it would be highly inefficient. You don't want to wait a minute for a job that takes 2 seconds. So if you have many small jobs to do, that too is a reason to bunch them up and use what you could call the subscheduler. So this same tool, GNU Parallel, that we will explain towards the end, will have a purpose here too. Bundle things up so that you can run things in parallel, even small jobs well. So here are some of the factors that come into play when we're scheduling things. There's a large factor attributed to priorities. So not everybody has equal priority on the system. And this isn't arbitrary or because we like people more. It's because there's an annual competition where research groups, PIs can say, I'm going to need about this much computation next year. Can you give it to me? And then we take that amount, which is usually a sizable amount, but given in terms of the number of cores you need for how much time, and we convert that into a percentage. We say, well, you want to run on what is essentially 5% of the system. But rather than just giving that 5%, we make that a target. So we make it such that people that have 5% of the system have a higher priority than people have 1%. And because of the way things balance out, if people keep things in the queue, like jobs in the queue, the 5% group will get 5% of usage, and the 1% group will get 1%. And so, but it averages out, and it requires people to keep things in the queue. So again, it's good if things are in the queue. Waiting is good in this sense because it helps with this. So priority is allocated once a year, and then there's a good chunk of the system that is not allocated, that is not given a priority, and so everybody else still gets a chance to run, even if they haven't made it through the competition. So it's not so bad. Another thing that matters is your past usage, and this again goes into the fairness. If a group was at that 5% level, but because some other group wasn't running, they managed in a week to use 10% of the system, the next week their priority goes down so that somebody else can use it. So that's a fairness thing. And another thing is time. If things are in the queue for several days, they will get more priority so that they will run eventually. So it's not that you will never run because your priority is low, you accrue priority. Obviously, available resources and the size of a job also matters. If you ask for, and this doesn't happen on homogeneous systems like the Teach cluster and Niagara, but on the general purpose clusters like Cedar, Graham, and Beluga, where they have many different nodes, if you ask for a node that has, and you want a lot of memory, there's not that many of them, so you're just waiting longer. So a scarce resource will take longer. But similarly, if you ask for a job that needs 40,000 cores, which is half of Niagara, you're going to wait a long time just for them to become available, right? So scarce resources or big jobs can be harder to schedule. And we try to weigh this a little bit so that larger jobs are pushed through a little bit better because this is supposed to be a system for that. But still, moderate resources can often go through the queuing more easily. In fact, very small jobs, like a single node or a single core for 30 minutes or so, like short things, might fit into a hole in the schedule. So the scheduler might have said, okay, here's where all the jobs are going to run, but I have like one node here that is not doing anything for 30 minutes. And then there's this low priority job, but it also only needs those 30 minutes. So I'm just going to put it there because there's no harm done. So this kind of backfill can be very useful as well. It depends on whether your workflow allows that, but it is a factor on how fast things are running. Okay, so the scheduler has to sort all of this out, list all of the jobs, sort them, and run the one with the most priority at that time, and it does that every minute. And so it's a busy little scheduler. But all of that is in the name of fairness. That's why it is. The waiting is for fairness. If you're waiting longer than another group, likely your group already used a lot, or they've been given an allocation and they need it. Now, to use a scheduler, so Slurm, there's a few parameters you will have to set. You can't get away from setting the time. You have to say how much time you want for your job. It doesn't have to be entirely accurate, because if it finishes earlier, that's fine. The job stops and somebody else can use that node. But if you run out of time, your job will be killed. So you want that to be an accurate estimate. The number of nodes can be specified with a dash capital N or dash dash nodes. The number of tasks with dash lowercase n or n tasks, or if you're running multiple nodes, it's often useful to use number of tasks per node. You can see how many threads you want. The difference between tasks and threads only makes sense when we're looking at the difference between shared memory programming and distributed memory programming, and I'm not going to go into that too much. What we will need here is just the number of tasks. Some systems you can request how much memory you want. Both Teach and Niagara don't need that because you always get the same amount of memory. It depends on how much the node has, and all the nodes have the same memory. So that's, but on other systems, this is a useful parameter. Okay, so those are parameters you put in your pound as batch lines, right? And then you give that to the scheduler. And there's a number of useful commands, and you can look them up if you look up Slurm commands. But sbatch is the one we use to submit a job. Sq is to see the queue. If you go, uh-oh, I made an error with this job, whether it's already running or still waiting in the queue, scancel with that number, the job number that you get when you say sbatch. Once your job is done, there is it gives you at the end some information on the efficiency, but there's a nice utility called SEFF, or Slurm efficiency, that gives a very short, brief description on what happened to your job, how long it took, what its efficiency was, like how much of the CPU time was actually used, how much memory was used. And so that can be useful to quickly check what happened to your job. And then those are all non-interactive jobs, so jobs that you submit to the scheduler and then run at some point. You can also get short interactive jobs where you get onto a compute node and you can type commands rather than have to have a script. On Niagara and on Teach and on Mist, debug job is a command that works for that. You just type it and you get some resources. Salloc is the general Slurm way of doing that. As I said, we don't need to do that here, but maybe in some of the other courses, this will come in handy. So I wanted to mention that. So parameters, commands, that's the scheduler. That's what it does. Okay. Now, before we end, let's go back to parallel processing, because this was just running on a supercomputer, and this happens everywhere. There are very few supercomputers that run without a scheduler, even if they might hide it. But now, suppose we have this problem of a load imbalanced parameter sweep, right? There's a utility out there that is very good at managing these kind of what we would now call subjobs. So a job is what we give to Slurm. Suppose that job has many different things to do, like those 96 runs of bond break. Those are subjobs. We just call them subjobs because they're within a job. And so to manage those, to run those on multiple cores, there's a utility called GNU Parallel. And the link is here. There's a good tutorial here too. And it's really just a Perl script. But when I say just a Perl script, that doesn't really give it justice. It is a well-designed and very versatile tool to run things in parallel, either over different cores or over different nodes. What you do need to do before you can use it, like almost any software, is do module load GNU Parallel to get the parallel command in your path. So here's an example. It's easier to see this with an example. So suppose I had some application. In this case, for the example, the application is called app. And let's say that it was compiled with the Intel compiler and it needed a library called GSL, which means I have to load some modules for it to work. But then in addition, I have to load this GNU Parallel command. Right? This GNU Parallel module gives me access to the parallel commands, and it allows me to run things in parallel. So imagine the parallel line was not here and the EOF was not there. What this would do would just run 200 jobs, changing directory to a job-specific directory, running the application, and then writing that the job is done. So this is 200 serial jobs. Instead, I'm giving these jobs to the parallel commands, and I'm giving an option here, -J, which says that I want to run a certain number of these jobs at the same time. Okay. Now, the sbatch or the Slurm specific part here is that instead of asking for one tasks, which we did before, we now ask for 16 tasks per node and 1 node. So we want all of these to run on the same node. This is important for GNU Parallel to work this easily. You need extra flags for it to run across different nodes. And so let's just do single nodes for simplicity's sake here. We'll run for an hour. I will give it a name. And so the number of tasks per node is set, and Slurm will put that in an environment variable that we can use here. So we can say that so this will be replaced by 16 just because Slurm does that for you. If you need less than 16, you can do that. Like suppose each of them takes a lot of memory, doesn't fit. You can make this any number you want. And then it runs, but it runs in the same way as I just, now I don't have the picture anymore. The same way as I explained in the load balancing, it runs the first 16. Whenever one is done, that core gets the next job. So it does the load balancing. So it assigns subjobs to the processors. And as soon as one of these subjobs finishes, it gives a new subjob until all the subjobs are done. Okay, so built-in load balancing. I didn't have the script around it. I just give it the commands that I wanted to run, and it runs it on as many cores as I tell it to run on. You can do it over multiple nodes. Usually it's better just to write separate scripts that use one node, but that's a technicality. Another thing that's very useful, because it is an existing application, it has other features. One of the features is that you can have it maintain a record for each subjob. So you can say, okay, here's a subjob. So you can see which subjob ran, how long they ran for, etc. The syntax is something you'd always have to figure out of a command first. You can give how many jobs run at the same time. So that's the -j. You can give a log file by doing -job log. Once you have that log, you can actually use it. And if you have a failed job, it crashed, and you want to resume and try the other ones, there's a resume option. So lots of nifty little extra things to manage these subjobs. Another nice thing that I don't want to not mention is that you can give Parallel all of these commands with this sort of here doc notation. So this is all piped into Parallel. I can also create these commands as a template. So I'm creating a template here that I give to Parallel. And then I pipe in what these the replacements of these curly braces should be. So this is totally equivalent, but rather than having to type this 200 times, I type the command once and then the parameters once. So that's kind of nice, this templating. Another thing you can do, once you have this templating, you can use a nice little trick. I really like this trick from Bash using sequence expressions. So if on a Bash command line, you type curly brace 1.200, it generates the numbers 1 to 200. They just substitute it for that. So I can give those numbers to GNU Parallel after this triple colon thing. And what it will do is it will look at all these parameters and one at a time substitute them for these curly braces, and then run those jobs that are generated that way on multiple processors. And doing this, you can also do a multi-dimensional parameter suite. So you could have two sets of ranges, and then rather than having just curly braces, you say whether you wanted the second or the first parameter from those ranges. So there's all the combinations in this case. So it can be a very powerful tool to do parameter sweeps. Okay, so we're going to use this because we have a parameter sweep. There's 96 issues. Let's see if they finished. Let's see. Okay. SQ user. Yeah, since there's no list, it must have finished. So let me look. It created sweep bond break output.txt. Now remember, we had that time command that actually shows you 3 times the real time, which is what we're interested in for every repetition, and then the user time, which is essentially the same as system time. We just care about the real time here. So every repetition takes a different time. This one took a bit more than 5 seconds. This one took 12, this one 3. So we see that there's a lot of variations in how long each of these runs takes. And so we will have some load imbalance. In fact, if I remember my job ID, here we go. I can ask it how well it did. And it'll say that I did very well, but that's not so strange because I run everything in parallel, right? So each of them themselves, each sub job is very efficient. But it did take 14 minutes, and we don't like that. This can be much, much shorter. Okay, so you're going to try and run this using GNU Parallel. That's going to be your assignment. Here we are. So your hands-on assignment, which I'm giving you now, it's also listed on the website. By the way, both the slides and the recordings of this lecture will be on the website. I don't know how long it will take to process the recording, but the slides are already there. And so what I want you to do is to take these 96 repeats of the computation and run them in parallel on a single node of the teach cluster. Now, the teach cluster, each node has 16 cores, so you should be running 16 things at the same time. Modify the, so first run it yourself. Time how long it took. It took 14 minutes and a bit for me. Make sure that that was sort of what you get. And then the best thing is to copy the script, the job script, to a new job script, and keep the old one for record keeping, and then modify it to use GNU Parallel and to run it on on 16 cores on a single compute node, and then submit that to the scheduler, and you'll again see how much it takes. So you saw that it prints out, it produces this output file that has all of the timings in it. That's the one we want. And of course, we'd like that to be faster than the 14 minutes than we had. So if you have any questions, ask them on the forum. We'll be looking at those. Tomorrow, come to the hands-on session. We have, which we have from 12:30 until 2. And we'll see how many people show up. You might not need answers, or you might be fine with the forum. That is okay. One thing before people started leaving, though, I should say that, or reiterate that we expect the attendance tests to be taken for at least 2 of the 3 events. So 2 of the lectures, say Thursday and Tuesday and Thursday, fine. All 3, also fine, or just today in the hands-on, as long as you also submit an assignment, okay? And again, to repeat, the answer, the code of this lecture was 4. So you still have about half an hour to take the test. Take the test on the website and enter the number 4. We have a deadline for this. It's not a hard deadline. You can submit afterwards, but we might not look at your assignments and might not have a chance to consider your particular issues or your brilliant solution in the last lecture. So please try and submit this by tomorrow midnight, or the way that the website rounds off times, it seems to be 11:55 p.m., but we won't hold you too much to that. Okay. We'll stick around a little longer to see if there's any immediate questions. But other than that, I will hope to see you guys in the forum and tomorrow at the hands-on, and then again on Thursday. Thank you for being here.